symbolic execution tool to achieve our goal. So in the first part, I will give a brief introduction about the KLEE. We pronounce KLE as Kili, so in the following conversation, I will just call it Kili. In the second part, I will let's retrospect some real bugs of QEMU program, and then I will list two methodologies which can help us to automatically discover any potential vulnerability. One of the two methodologies has been adopted in the Denserver project, and actually it has helped us to find some bugs inside the QEMU DM program. We find some buffer overflow from the VGA device model and IDE device model inside the QEMU DM program. And at the same time, we also find the weakness of the first methodology. So now we are investigating a new one, the second one. In order to make our idea clear, so I will introduce how QEMU DM works, and then I will talk our idea in a detailed manner, and finally I will talk something about what we have done and what we are doing. Okay, first, let's see the Kili. It's a symbolic execution tool, and it's open source. On the top of the page, we can see a link. So if you are interested, follow the link to get all of its source code. And on the left part, I list a very simple program to demonstrate how Kili works. So you can see the first step, we need to make the import of a function to be a symbolic import. And then we need to so just look into the right part. So after we change the source code, we compile the C source code into the LLVM bytecode format. Because Kili only recognizes the LLVM bytecode format, not the binary format. I know that some other tools like FastGrind will recognize the binary code, but don't like the LLVM bytecode format. Then Kili core engine will load the LLVM bytecode and symbolic execute the code instruction by instruction. And if it runs into a conditional code branch, it will request the constraint solver to give it a solution. Maybe sometimes constraint solver will tell the Kili core engine there's no solution, but sometimes the conditional code branch code statement would be true, but sometimes it would be false, and then Kili will fork into two code branches and clone the current execution context into the two code branches, and then execute the two branches separately. Finally, Kili will output the symbolic import value, so which covers all of the target programs code passes. Here the output is calculated manually. They are not outputted by Kili. So here is the real output, the real execution process exploited by Kelly. So we can see it generates 4 test cases, which covers all of the code passes that is contained inside the simple program. Now let's see in a detailed manner how Kelly works. First of all, we need to compile the target program to LLVM bytecode, and then the Kelly core engine plays as a role of virtual machine to execute the LLVM bytecode. The core engine will traverse as many possible as code parses in a given time budget. And it has several options, several different options to traverse the code passes, like the depth first search, breadth first search, and non-uniform random search. And it also provides some optimization, like query cost optimization and code coverage optimization. We can combine the different search approach and with the optimization. Someone may think out the problem. What will happen if there is a data loop inside the target program? Actually, even in theory, we have no good approach to handle to identify and to skip the data loop inside the target program. So for Kelly, it has no good answer either. And if during the code parser traverse, if Kelly core engine runs into a conditional statement, it will request the constraint solver to give a solution. Sometimes the conditional statement just be true all the time or be false all the time. But sometimes a conditional statement will be true in some cases, but in other cases it will be a false. And since Kelly depends on a constraint solver, and the constraint solver doesn't support the symbolic sized objects, so actually Kelly has a limitation about it on the symbolic sized objects. What is a symbolic sized object? So just imagine that we call malloc in our program, and the argument size would be a dynamic value, but not a fixed value. So in serial, it will a lot of there's sorry. In theory, the dynamic variable size has maybe it equals to 0, or maybe it equals to some very big positive integer. And since the constraint solver doesn't support this case, so Kelly does some workaround. So when Kelly encounters such a case, it will request the constraint solver to give a minimum value and a maximum value of the size variable. So then it will try to allocate try to do the memory allocate with the minimum value and the maximum value. Sometimes if the maximum value is too big, then it will fail to allocate the memory block. So then it just skip the case. And someone would say that, so how Kelly handles some external function call like libc open, close, read, write, or whatever. Actually, Kili is embedded with UC libc. So for these libc functions, it is okay. Kili can handle this. But for what about the system call interfaces like fork, exec, or clone? Actually, Kili provides partial of the external environment modeling, like the file system access. But for the fork, exec, these system call interfaces, Kili at the runtime, Kili just prompt a warning message and then return value, which means it is successful. Finally, if code parse reaches its end or something error happens, then Kili will generate a test case and iterate the test case into a file, and then we can replace the test case once the Kili code check is completed. Someone would say would maybe think that the previous sample program is too simple, and maybe someone would say, oh, it's cheating. Actually, here's a real example about to demonstrate the capability of Kili. Kili generates a command line and imports to the programs inside the core utilities, and it succeeds to find some real bugs inside the programs of core utilities. So if you are for some detailed information, you can follow the link to read the Kili's paper. Okay, now we have a rough impression on the Kili. Now let's retrospect the QEMU program. I picked up 3 real bugs from the common vulnerability and exploitable database. You'll see what if QEMU has a buffer overflow issue, and it is highly possible that it may cause denial of service or root privilege escalation problem. So then one question comes out. So is there any idea to spot any potential vulnerability automatically? Here we have 2 methodologies. One is force testing, and the other is symbolic execution. Actually, the first one is easy to implement and deploy, and we have adopted it in the Zen server project. So we just construct a Linux kernel module and deploy it into our Linux HVM guest, and then the kernel module will keep running and feed some random input to any valid I/O port, and then another monitor program checks if the target QEMU DM program crashed or not. Actually, we have found just as I said before, we have with the help of the force test, we have found some real program of QEMU DM. But in the meantime, we also find the weakness of this methodology. First, it is there's a very hard time reaching some code parses, and sometimes different random input will reach the same code parse, but we don't know, and consequently we don't know how about the code coverage. Maybe our scam just cover 10% of the QEMU code. or maybe it covers 80%, but we have no idea. And the second thing is that it is not reproducible. I mean, we need to keep a record of all of the random imports. We need to keep the random import sequence. And then if we want, if a real crash happens, we need to replay all of the import seed inside the sequence. Then we can see the QEMU program crash again. But in the reality, it most likely it causes 2 or 3 hours, maybe more, to trigger another crash of the QEMU DM program. So it's really it's really inefficient. And now we are working on the new methodology. So we leverage the Kili as a symbolic execution tool to do the QEMU DM program code check. So since the Kili has the internal state representation of the QEMU program, so we suppose that if a test case import has reached one code path, then next time it will not go through this part, because Kili has the knowledge of the internal representation about the QEMU program, and Kili has the capability to generate a stable test case to reproduce any code fault. So it can solve the non-reproducible problem of the fuzzing test. And so Kili has a higher code coverage, so which fuzz test doesn't have. But the problem is that it is not easy to adopt this methodology. In order to understand our idea, let's first see how QEMU works. Sorry, here I only cover the QEMU DM program. Actually, QEMU DM and the QEMU program, they are a little different. On top of Zen or Zen server, QEMU DM program pulse keeps supporting the IO request communication channel, which is a shared memory block between the QEMU program and the hypervisor. And then if there is IO port read-write or MMIO read-write instruction which is happening inside the HVM guest OS, then it will trigger a VM exit event. And then after that, then hypervisor will take the CPU's control, and hypervisor will package all of the request information into IO request, and then put it into the shared memory block, and then notify the QEMU program to handle this request. And once the QEMU DM program gets the chance to run, it will fetch the IO request and serve it, and once it completes the request, it will notify the hypervisor, hey, I have done the job. Here the content is just I described. So I don't want to read the content line by line because it's really boring. So QEMU, here I only talk about the QEMU DM program. For QEMU program, it is a little different because QEMU doesn't depend on Zen server. on then or then on the hypervisor. Sorry, QEMU program accepts the import from the OS image. It reads the instruction. It reads the import instruction by instruction and emulate it and do some and then interact with the target system. For the QEMU DM program, it accepts the I/O request from the shared memory block. So we can see that actually the Kili cannot fill the import directly into the QEMU or QEMU DM program. So it's not easy to adopt this methodology directly. Now I'd like to illustrate our idea on how to adopt the Kili to QEMU program. Why only the QEMU program? Because QEMU DM depends on some more external libraries than the QEMU program, such as the libxc. So actually, Kili doesn't do not know the libxc. So when it runs into the libxc code, libxc function call, it has no idea on how to do it. So our first target is only the QEMU program, not QEMU DM program. So our idea mainly contains two steps. The first one is we will prepare a minimum QEMU image. It contains its size is very small. It only contains necessary load or startup instructions, like the startup _64 inside the Linux kernel, something like that, and some I/O port in and out instructions. And then the second half is run check. So the Kili core engine loads the QEMU LLVM bytecode and the minimum OS image, and then Kili generates symbolic import and traverses the QEMU program state space. One thing that current Kili doesn't have is that we may need to change the Kili to record all of the import sequence. And another thing needed to change is that in serial, Kili will not crash, even if the target program crash. But we are not sure, so maybe we need a watchdog timer to monitor the Kili program. If some error happens, we need to restart the Kili code check process. And currently, Kili depends on some external tool like QEMU code coverage to generate the final code coverage result. And here we needed to change something to make the Kili automatically to output the code coverage. Here we have an alternative option. So we may start a QEMU program from an actual instruction trace and treat various instruction arguments as symbolic import. See if some import causes error, but this requires much change on the Kili program. So currently it is not on our target. Maybe in future we will take it into consideration. Finally, let me introduce what we have done and what we are doing. Actually, the first part of the work has been done. So Paul, the first name on the first slide, has achieved to use Kili to boot boot the toy OS image and do some initial symbolic import check. So, but if we want to do the symbolic execution on the QEMU DM program, then we need to consider that how to remove some dependency like the libxc. Maybe we need to provide a stub libxc or something else. And for some other parts, we are still on the way. The first one is that how to map the symbolic import to the instruction import, because QEMU program doesn't recognize the symbolic import. So we may need to change the QEMU program, and at the same time we need to change the Kili source code. And another problem is that if the QEMU program crash at a location A, so then we started to execute the QEMU program. Maybe it's a crash at the same location. We are not sure, but it is likely. And it is likely that there are many other problems that we have no idea currently. Okay, that's it. Thank you. And any questions? Please.
One of your slides indicated that there were some limitations due to.
You mean KLE, right?
There were some limitations where you ran into code that used malloc, for example.
Mm-hmm.
It seemed that you had some mention of possibly using some arguments based on some runtime evaluation. Couldn't you also initialize some static data structures that you would basically do by code inspections immediately in Kili, so that we can actually proceed move forward? Is that being evaluated as a possibility?
Sorry, I don't understand your meaning.
So you seem to indicate that there's some limitations in Kili when you use malloc. Is that right?
Yeah.
I was curious whether or not you can actually provide a static data structure as a key to Kili, so that we can continue to assume that you provide essentially the information necessary for it to move forward. Is that a possibility for you guys? Or?
I think maybe it is difficult to do that.
And how many bugs have you guys found? How many bugs?
You mean by first testing or by Kili? Currently, no. We haven't achieved the final result. But for first testing, we have found 4 to 5 VGA device model bugs and 2 IDE device model bugs. Okay. Thanks, everyone.